search artifact and building block of modern machine learning. So why so-called foundation specialist models may become obsolete or are not even a thing, and why it is important to have entire pipeline for building foundation models open source. So first, a little bit of history, because the field, meanwhile, is not as fresh as just 1 year. And it's important to understand where we come from. So the old machine learning has decades of history on its shoulders, I guess at least since 40s. And in 80s, 90s, zeros, we had this old machine learning classical field that had this narrow, non-transferable ways to deal with creating models for solving various kind of tasks. So the problem of that was that usually you had per task, per data set, per setting even, just one model, one specific algorithm. Algorithms were even different across different task conditions, and you were ending up with exactly one trained model that could perform in a very narrow setting on one task and was immediately collapsing if you were trying to go outside of this setting. So that went for a while like this, and people were a bit losing hope. So the new hope then came in form of what people have called deep learning. First breakthroughs with that happened in supervised learning setting around 2010, 2012. One important part behind this breakthrough were large-scale labeled data that had broad distribution in contrast to previous history. So data sets that are meanwhile classical, like ImageNet 1K, 21K, played a major role. It was a large community effort to gather them together, 5 years, driven by Li-Fi from Stanford and others. It had finally a unified learning procedure, so the multi-layer neural networks of different kind, that were not so different in the end, were the unifying building block here. And finally, people managed to get rid of this handcrafted task-specific priors and features that had to be engineered very painstakingly each time before. So this delivered finally something that could be called transferable across datasets and tasks in proximity of the training regime, and something became possible that was not possible before, namely efficient few-shot transfer. So you could fine-tune what you have pre-trained on specific domains and tasks with rather small data. So zero-shot transfer, so immediately adapting to the task, was still not working well in the setting. So as mentioned, the whole major breakthrough line in our field in core machine learning is usually bound to scaling up and increasing the diversity of the data distribution behind the training. So here it was no different. We went from this very specific handcrafted smallish data sets to large web scale ones. And now we had this way of having so-called pre-trained backbones, so models that could be pre-trained once on such data and then transferred via way smaller scale fine-tuning procedures across different settings of interest. So the evidence that this procedure is actually outperforming strongly something that you would build just for your specific tasks. So taking a special algorithm for this one task only, special data set for this one task only, came quite early back then, 2012-13, with models like Overfit and VGG16 that were somewhat immediate successors of AlexNet. And they were providing so-called off-the-shelf transferable models, so you could take them. So here in the plot, those are painted in pink or red. And you can see that for every specific setting of solving a particular task that was usually then required to develop something from scratch that is specialized tuned for that in green, they were beating state of the art just with one method. pre-training large and then transferring with a little effort across all of the settings were giving a better performance all of a sudden. So that was encouraging. People then started to look more closely into this, more systematically constructing actually test data sets that were resembling this transfer scenarios. So this work VTAP presented a number of those. And what people saw then again here, training from scratch, meaning that you attempt to build again a specialized model by taking just the data relevant to the task and nothing else. So now using the same algorithm across the conditions, namely the deep neural networks in this case. And people saw again that it is worse in this older, meanwhile, supervised pre-training setting to pre-train first and transfer than just doing it from scratch on specialized data. So it was back then also quite unintuitive, and still for many is. Why would you do something completely non-task related for pre-training and expect benefit from this? So this is the empirical finding that holds across very different domains and is still an open question to investigate further. Why is that the case? So pre-trained and transfer being stronger than training from scratch on the data of interest. Then further evidence came in stating that the smaller scale models might strongly lag back in comparison with larger scale models when you do this kind of a transfer. So here on the x-axis, you see different pre-training data sets arranged from left to right according to their size. So ImageNet 1K, 21K, and the closed data set that's not available publicly, GFT 300 million, collected by Google. And the smallish circle depicts a smaller scale model that transferred across these three settings from left to right, ImageNet 1K, PETS, or Cypher 100, struggles to have any substantial win from increasing the dataset size. Whereas the larger circles, like the faint blue one, you see the steady increase. So this was the first hint of caution to be not falling into the illusion that increasing data scale might be useless after all if you work on small scales only. So to see the benefit there, you have to also invest more in model scale and compute accordingly. So in this evidence continued to appear in a number of various other works. Here another example where you were seeing the same story roughly, so that the pre-training and transfer strongly outperforms training from scratch on specialized data, but only for larger models. So training on specific data from scratch matches pre-training and transfer, but only on smaller scales. As you see the overlapping lines in orange and blue here, you don't see a difference up to certain parameter numbers on the model scale size. And this match happens in poor performance regime that you actually also not even interested in. But the most experimental settings are happening there because it's cheaper to operate in that regime. And so people often have this illusion of small specialized models being as strong as the larger ones. But this illusion is only because you don't actually look further on what happens if increasing the scale hand in hand. Where the pre-training and transfer starts to clearly beat, strongly outperform training from scratch on specialized data. So this efficient transfer after the first wave of breakthroughs in supervised setting was enabling now training once large, somewhat inefficient, and then performing way more efficient transfer across different domains using this very same pre-trained model across different scenarios with little effort of fine-tuning invested for each scenario. And importantly, also small scale data necessary for each transfer. You don't need to go large anymore. In domains that made the breakthroughs that were considered classical computer science domains, so computer vision, natural language understanding, the insight came in that you don't train specialized models. You also train generalist and transfer, and you beat any specialized model that you were aiming for. So this is, of course, a bit of an exaggerated example. So we don't train any more cat models or car models or face models or chair models. You can replace this now metaphorically with a domain, so medical, material, and so on. You train on everything that you can broadly obtain, and this is a very large data collection effort in the beginning of each generalist foundation model attempt. And then if you are ready with the data set that is generic enough, you can obtain your generalist model and begin to transfer strongly. So to some degree, transferable learning was installed in this setting of supervised deep learning that required labels, though, still for all the samples in the data sets, and that naturally limited the scalability of the data. So you can, of course, crowdsource data labeling, but there is so much you can then label per hand, right? There were clear problems with robustness of these models. Adversarial examples came up, showing that you can only slightly change the samples after training, and you are changing the model behavior very strongly by doing this. So this is like an Empire Strikes Back moment where people understood that although way more transferable than the methods that we had before, there are still clear troubles, and zero and few shot transfer regime was still performing very poor. And what happened then is that people found a way to give up a largely supervised training setting and come to something that we meanwhile call self-supervised, where labels are discarded entirely, and you digest basically the data as it comes, also multimodal. So language with any kind of additional modalities, vision, audio, can be fed into such training algorithms as a sequence. And following a generic pre-training in this regime, you can then transfer to various conditions and tasks, and now you can transfer also well in zero and few shot regime. And importantly, so natural language provided the breakthrough to serve then as interface for flexible formulation of any task in zero shot mode. So you can prompt now this pre-trained generalist models with any task you like, and often enough, without any further adaptation in zero shot, the task can be solved to a way more satisfactory degree than it was possible before. So advanced functionality like in context learning appeared that requires you just to put few examples on the input of such pre-trained model, and it will be able to decipher what we'd like to do further on with the task. And importantly, this class of methods now started to clearly exhibit scaling laws. So their core capabilities, transfer, especially zero and few shot transfer, were improving when scaling up the pre-training. So we had here then this kind of a core breakthrough that led to the artifacts we meanwhile call foundation models, where you had now scaling law describing that given one and the very same algorithmic procedure, you can invest into scale during the pre-training, and you will get an increase in core performance across different tasks of interest. So the training is happening also now in mainly task agnostic way. So you do not incorporate any task specific priors like before. The evaluation finally becomes standardized, so we can now also compare the models in way more reasonable manner than it used to be before, where everybody used their own favorite benchmark that nobody else was recognizing. So the community progress becomes also possible due to this standardization. And we have strong improvements in model robustness. It doesn't collapse so easily anymore. So one example how this number of breakthroughs came in place is well explained on here, the specific case of language vision foundation model called CLIPS, or contrastive language image pre-training, a self-supervised training algorithm that uses data on a public web scale that is composed of image text pairs, where image can be accompanied by any kind of text. So importantly, these are not labels anymore. So you do not provide those as supervised signal. You just feed the image and text along as one sequence. And importantly, the text as caption can be as noisy as it gets. It can have like erroneous information. It's surprising that it works this way at all, but it does. So you feed the image and text together as pairs, and you drive the learning by a very simple loss that tells that if image and text are appearing in the dataset together as a pair, then you construct a positive pair out of it, trusting that they belong together for some good reason. And then you shuffle the images and captions against each other and create a lot of negative pairs that give an additional pseudo label of not belonging together as a signal to the learning procedure. So this is enough to ignite learning on web scale data in the right direction, which leads then to a strong pre-trained foundation model that in zero shot is able to outperform anything that was done before in deep learning. So you see a zero shot performance here with a star on CLIP that is way above by a large margin on the classification tasks compared to few short attempts that were here for comparison put in different colors by the methods that were before considered state of the art. So importantly, it was also increasing the robustness of the model. So when people realized that after training, the methods can behave in a very fragile manner, they constructed specialized data sets to test the robustness of a model. Here, an example of ImageNet by creating various ImageNet derivates like ImageNet V2, R, ObjectNet, ImageNet Sketch that were actually containing the same classes, types of object as ImageNet, but in various distorted variants of this. So, and in the previous supervised deep learning, you are seeing a strong collapse of the model performance if confronted with such datasets after training. So you see here on ImageNet ResNet 101, it was considered to be a large-scale model before the era of proper foundation models came up. You have 76% classification performance on a validation set of ImageNet, but then you have a strong drop up to almost zero, like 2.7% only on ImageNet A. This you don't observe anymore in web scale pre-trained models like CLIP. And importantly, so and you see the gap is huge. It's 2.7 versus 77.1%, and this is a zero-shot regime, so you don't even adapt to these data sets. So this is an important notion here. You can adapt models like CLIP further on by fine-tuning. The performance will increase there, but already in zero-shot, you staggeringly outperform everything that was out there before. So in this, again, to emphasize this type of breakthroughs are again possible by increasing the broadness and the diversity, in the end, the scale of the data sets that were used for the training. So not only the compute and the model that is used in the pre-training, but also the data set has to go the same direction of scaling it up. And here, of course, even more, the insight was we don't go for training specialized models from scratch anymore. So we train large generalists, then transfer into much smaller specialists by way more efficient training procedures than the pre-training itself. So we don't go for anything like cat and car models anymore. We have vision generalists that can be then adapted to any scenario further on. So now the one of the most important points here about foundation models is the scaling law exhibition. Back then surprising finding was that if you take So if you indeed have a foundation model, then you have an algorithm that belongs to this class of scalable learning, which means that you can, from the same formulation on, scale up in both compute, model, data set size, and then you will see the smooth improvement of core performance metrics that you're interested in while scaling up. So without changing anything in the core algorithmic procedure, you get gains. Conventionally, the empirical observation was that this is a power law function of any dimension of the scaling up, compute, data, or parameters. So this is the plot from a meanwhile classical paper by Kaplan et al. From 2020 on language models. So this scaling laws have not only established the surprising finding that you can just get gains by scaling up, which was not happening before in this form, but they also allowed to predict model properties and function across scales in a rather accurate manner. So especially compared to what possible before. So once scaling law is derived in proper form by executing the experiments carefully, you can also have predictions that go 2, 3, even sometimes 4 order of magnitudes beyond the scales that you are observing in the experiments, and have an accurate prediction what you would find there. And importantly, also not the performance prediction, but also the prediction, how do you set up the algorithmic procedure itself, what hyperparameters you should take, what model size, what data size should you invest in to have so-called compute optimal outcome from your training procedure. So you don't waste the compute on the procedures that have a wrong configuration and are suboptimal. So these predictions turned out to be so accurate that in the few, usually back then industry closed frontier labs, as the name goes, people were using this method before they were then doing their moonshot training, so to speak, before going this 2, 3 orders of magnitude up. So that became a standard method to investigate the properties and function of foundation models. And so the problem was back then that foundation models became indeed this core research artifact and building block of many other downstream methods in machine learning field. And scaling law study became also a standard way to investigate why these properties are exhibited, how we observe them. And so the few people who could study this were those sitting in the closed industry labs, few of them equipped with resources and skilled people that were able to do these experiments. In academia were not even properly able to replicate any of those artifacts and study them properly. So that was quite a weird situation for a scientific field. And as major, large scientific organizations were not catching up with this, out of despair, that led to a rise of grassroots research communities that were attempting to open source and study foundation models and data sets on the interesting scales required to understand what is going on. So Illusory AI in US appeared and dealt with language modeling for a while, so constructed data sets that are very important for the community, like Pile. Back then in 2020, invested also a lot in standardizing evaluation routines. So the software stack called the Lemmerval harness is meanwhile something like industry standard. Big Science in France was incepted around Hugging Face efforts that were also trying to get our community around to replicate back then GPT-2 and 3, leading to Bloom initiative that were taking public funded supercomputer Jonsei to do this experiment. So Lion in Germany was founded 2021, quite parallel to Big Science efforts that focus from the start on multimodal foundation models, so language vision, language audio, collecting the data sets and training the corresponding models, studying the scaling laws, attempting to get the full pipeline as open as it goes for allowing broader research community to access it. So, and this is indeed something that is meanwhile, the main point of the efforts, making a whole pipeline. So importantly, data set composition, data set itself, model training, benchmarks, and evaluation fully reproducible. Um, uh, when people begin to make use of the notion of open source in machine learning and AI, this is what it has to mean. So the full pipeline being as reproducible as if you think about software open source. So you can have every bit changed and every bit is accessible to scrutiny and validation. Um, we have, meanwhile, a couple of such pipelines available for important foundation models, for instance, for CLIP with Line 405B, Reliant, Datacomp as data sets. OpenClip is a open source training code base that can work on supercomputers. OpenClip Benchmark is a repository that standardized the way how to evaluate this. And the same happens also for language models. So meanwhile, not only Luther AI, others have catched up. So our own work on DCLM baselines with Stanford and University of Washington, work by Allen AI Institute, so Olmo, and of course a lot of Chinese research labs that produce the open weights models. So usually they don't release the data sets. So this is then a major trouble and cannot be also called properly open source. So this open pipeline allows you then to go and derive the fully reproducible scaling laws for important types of foundation models, which also opens the road for proper validation of the claim that this is actually a foundation model, and also comparison across various learning procedures of a similar kind. So here, our work was dealing with CLIP, was taking the open data that we have collected, so the line 400M and 2B, and comparing it here in the blue line with the closed data that we couldn't touch, collected by OpenAI. And we could, to some extent, align the learning procedures precisely so that the only difference was data. So that was also the first time that we have seen that, of course, as expected, but you have to measure it as a scientist, data set has very strong influence on the scaling law form, although from the 3 points that were available on the OpenAI side, you cannot conclude much, but still you see across different task scenarios. So here we have compute axis on X, and on Y we have a zero-shot ImageNet classification error rate. We see that seemingly the OpenAI data set leads to somewhat stronger scalability. So the line is stronger tilted that you feed through this. Well, 3 points. And for the different task retrieval, so you can measure scaling law across through very different tasks, and you should, to make sure that the trend is observed across many downstream scenarios and not only one. So here you see that the blue line, so the closed data set, is weaker scalable. So for the first time, and this was also, I think, an important point of the study, there was the hope there that not only a few hyperscalers can perform this kind of experiments, but also academic labs can catch up if gathering the right amount of skilled people and resources to execute experiments and organization behind this, it works. So it's not a hopeless endeavor. It is very well executable. And in that sense, back then, Lion became also an open frontier lab, because with the OpenClip reproduction, we could show that we match or outperform the closed lab frontier models, and in some sense deliver also better results scientifically on the top by providing this fully reproducible scaling laws that were not derived before. Importantly, this kind of open source work also leads to usually explosion across the broader community. So our work, the data sets, and the pre-trained open clip models were taken by others. So Stable Diffusion, for instance, is another very strong open source project, made use of it. And you also see the impact of such studies by coming up very strongly on the venues that matters in our core research field, like MERIPS. So this work also gained outstanding paper award there. Another important indicator that such work matters for the community is then the number of provable reusage of such artifacts. So the open clip models are still downloaded a couple of million times each month, and then we have more than 100 million of downloads of these pre-trained models since their appearance. So even older models are still useful in both scientific and industry sense here. So, okay, reproducing something and providing better insight in previously closed models is one important step. Another important step is, of course, improving on the top of it. It's clearly that, well, the reproducible pipeline is the prerequisite for any improvement, as otherwise you cannot even reproduce it. But the open pipeline allows you also to think about further experiments to actually make the existing foundation models better. For instance, improve their scalability. So tilt the line that you observe on the scaling plots even further, so that you gain more for the compute invested during the pre-training than possible before. So here, the question becomes, how do you actually execute model comparison if you have existing foundation models that already perform to some extent well? How do you compare it to your claim? Basically, I have an intervention X that makes it even better. And it is actually a problem, which I try to show off why on this small toy example, which is actually not so toy because it happens all the time in the real setting scenario. So if you imagine that you have some procedure that already exists and leads to a provenly foundation model type with scaling laws and whatsoever in orange, and you would like to suggest, assuming that this procedure in orange is open enough so that you can take and build upon it, you are thinking about a number of interventions, XY, that will lead you to somewhere, to a blue model. So procedure in blue depicted here, you then put them ideally, best practice goes on the same aligned compute axis during the pre-training so that you don't cheat on yourself by just investing more compute and having better performance. It's not due to algorithm, but just more compute went inside. This is not really so interesting anymore. So we don't want just to scale up. We want to have something stronger scalable here. And you observe this bluish points having here on y-axis is test error, so the lower the better, having an advantage at the two fixed points that you have being conducting measurements. So the problem with it is there are a lot of things that you can change along such a pipeline for creating a model. So it can be a data set change, it can be the architecture change, it can be just simply some hyperparameters. So we assume that we tuned for every setting as far as it goes, so we don't have just a simple hyperparameter mistuning explaining the difference here. So we actually cannot know so straightforwardly what caused this difference. And even more importantly, we don't know whether this difference will actually propagate to the performance range and to the scales that we haven't seen before. So as you see here, we are still at the rather poor performance regime where the test error is high. When we observe an advantage here, we can be happy in this particular test regime. And if the achieved performance here is sufficient for our task, we can stop, of course. But usually it's not the case at all. The case usually is that you would like to achieve performance that is way better. And you are interested then, of course, what will happen if you invest more compute into the scalable two procedures. So, and what can happen, and this takes exactly the same points that I was showing you before, is that if you then go and attempt to derive a full scaling law for this using the both learning procedures, you will see that at some point the lines will cross, and that they actually advantage of the bluish procedure on the smaller scales entirely goes away and results actually in disadvantage in the larger scales. So comparison using the single isolated points can be highly misleading, especially if executed at the scales where you are not really interested to perform on. The way to compare between the procedures should then include indeed the way to have accurate predictions in what happens afterwards and avoid this kind of an illusion. It's just zooming in into this plot that we had before, where you have, if you just look at the small span on the smallish scales, actually the performance regime where you're not of your main interest. So how to do it in practice? So we have now some recent insights how it can be performed, done on the language vision learning scenario using CLIP and extensions of CLIP. So this paper now recently appeared in NeurIPS, and I would like to go quickly through it to create an impression what it takes to conduct such a model comparison. So here the setting is that we have the well-established foundation model training procedure, which is CLIP, having pure contrastive loss, image and text towers, where both image and text input comes in, and computing contrastive loss on the top. And you can have various spin-offs of it. For instance, adding a generative text loss to the text tower, which makes this model, in addition, model capable of captioning images, generating text. Or you can have a symmetric version where you also generate image tokens and potentially can also create images. So the question becomes then, is it worth actually driving a learning procedure with this additional losses, or is the contrastive procedure actually already good enough and you shouldn't bother? So to answer these questions, as hinted before, we can derive scaling laws for the learning procedures in a situation of fully open pipeline for driving training, and just have a look what we obtain. So to derive the scaling laws, we need though to span quite a large grid of different model scales and sample scene data scales, where we for each such a point have to perform a training procedure. For smaller scales, it's cheaper. For larger scales, it's not so cheap anymore, but overall, it's way cheaper still than going to the target scale of interest. And importantly, for each such a combination, you still need to tune the hyperparameters to make sure that you don't have distorted measurements due to improper tuning of the learning procedure. So once you performed the measurements of the kind for each learning procedure of interest, you obtain something like this, where you can actually then fit a scaling law for each of them. In blue, we have now Mammoth, and in green, we have the CLIP, both aligned on the same compute axis X. And here we see two different downstream tasks that are usually the gold standard to measure: the zero-shot ImageNet 1K classification performance error rate, and retrieval zero-shot as well on the right on MS-COCO, another test data set. And what you see here is a rough resemblance of the toy scenario I was showing you before, that we have quite a clear advantage of the green CLIP versus Mammoth, so CLIP extension with text generative loss and smallish scales. And if you would measure only there and don't bother to estimate the trends, you would actually conclude that it's not worth dealing with the extended procedure at all. But what we see then in the end is that if deriving the full scaling law, it can actually quite well catch up with predicting the crossing between the two lines, and actually predicts the blue mammoth as a more scalable method that will outperform the green, the clip, in the larger compute scales. So to make sure that you can actually trust this comparison, you have to double check whether the predictions delivered by the scaling laws are worth something. And this we do by taking the measurements on the held out points that we do not use for the fit of the scaling law, and then obtaining the predictions on the rest of the points that we fit through, comparing them with what we actually obtain if going to the held out points. And we see that if we see that predictions are accurate enough, then we can begin to trust into validity of such comparison. Another way to ensure that the comparison is to be trusted is to make it across different scenarios using the same procedure. So again, scaling law derivation using a different data set. On the plot before, we've seen data comp. Here we see a reliant, different data set composition, same qualitative and even to some extent quantitative outcome. You have an advantage at the smaller scales for the blue, for the green, for clip, and then mammoth in blue takes over. And the crossing point is even having a very similar position comparable to the prediction before of around 10 power to 11 gigaflops for the pre-training compute. So you can also do dataset comparison, same way how we did the model comparison. So clip versus mammoth before. So now we have 3 different data sets, all open, all reproducible. So we have a reliant, data comp, and DFN in violet, red, and yellowish. And we can then, for each learning procedure, clip on the left, mammoth on the right, derive scaling law, now replotting the same measurements which we did with regard to the data set that was used. And what we see now nicely is a kind of a data set ranking that is all given through the whole scale span. So we can be sure here that, for instance, the FN is a preferable pre-training data set clearly on the larger scales. And again, if you look on the smaller scales only, you don't see actually that much of a difference. So, as hinted before, this type of scaling laws are not only good for stating that you have a foundation model, reassuring that you will gain from scalability. It is also good to predict the actual performance that will happen on the larger scales that you don't see during the experiments. And we test this also in the study by actually going to a predicted, to a larger scale with predicted strong performance, training open mammoth L14 on 12.8 billion samples from data comp 1.4 billion, catching up with even closed models that were trained with way more compute, like Siglip by Google. And we can see in the trend that if we invest actually comparatively similar amount of compute, then we will match again or take over. So the Siglip was trained on proprietary data that is not released, Webley 10 billion. Here we have, of course, the advantage that anybody from the research community, if applying for a compute grant on one of the public supercomputers, can actually reproduce the full story and check up whether these findings are correct. So, so far to the way how one might perform model comparison using scaling laws. The weak point of this consideration is, of course, the trust in the evaluation procedure itself. So that what we see on the y-axis is usually a form of standardized benchmark that poses a downstream task with a test data set that measures some capability of a model that considered to be a proxy for anything that you would like to know. So ImageNet 1K performance, the zero-shot classification, is known to be a proxy for I have a strong model in front of me and I can transfer it well to different downstream tasks. The fair question is, of course, whether this is actually true to a large extent. In language model community, this is the same kind of a problem, of course, where you have to come up with standardized benchmarks, testing the core skills of any presented language model X, and using then the scores, you can either trust or not trust the assumed performance of the model in your hands. So in language model community, then there is also a test battery, same way how we have it in Vision, consisting of the number of gold standard benchmarks. And here you have an example of evaluation that people usually are doing. So on current reasoning language models of larger scale, you have those test sets like AMI or GPQA or code forces that present actually very complex problems to solve on the level of high school Olympiads or even sometimes higher up, where the tested models of different kinds, so here a number of frontier models are presented, achieve high scoring. So we were asking the question to what extent you can actually conclude that the models indeed have the strong capability, and we're operating then with way simpler problems to see how much trust you can have in the scores actually measuring what you are interested in, namely something like core generalization capability of the models, working with these very simple problems in natural language formulation that arguably has a character of elementary school and requires elementary arithmetics to solve them. So what we see is that we still have to work on evaluation properly. So these scores are not exemplary for reflecting properly the generalization capability of the models. Here we see that actually quite strong, even closed frontier models have problems in addressing this task of particular kind, namely, if you just introduce natural variation in the simple task formulation, just simply varying the natural numbers across the problem instances, you have very strong fluctuations in performance rate, how successful this task is solved. So like for GPT-4, here on the right, you see that for some reason, for the variation 4, you have actually it is 100% correct rate solution. But for the variation 3 that has absolutely nothing changed in problem difficulty and structure, you have all of a sudden collapse almost to zero. So this should worry you because it hints that at least for zero-shot generalization, you have lack of robustness in these models. If they would understand the problem correctly, of course, there wouldn't be any fluctuations across these variations anymore. So it might be that the high scores that we see on different types of this difficult problem test sets is because we have training data contaminated with many of those tasks. And we indeed see some of rather direct evidence that it is the case. If we vary this simple problem formulation just a bit, here displayed in the above and the below task variations, we see something that might be called illusion of the strong function. So as Claude 3.5 Sonnet has appeared, we were testing it on the two variants of this problem. And you see on the left that for the one problem type, it solves across all variations almost perfectly. But for the other problem type with just slight variation, it collapses to way lower performance. So Again, this is a hint of a weak generalization capability, even in this kind of elementary school simple problems. And you can replicate one of the possible reasons why it might happen by fine-tuning an open weights model. Here we took llama 3.18b. You see on the right side here in A, it cannot solve the task at all in its original form. And B, if you fine-tune it, a lot of variations get almost perfect correct score rate. But if you then go away a bit from the fine-tuned problem formulation to the formulation number 2 I was showing before, then you immediately have a collapse again. So you have to decontaminate definitely the training data before you make any conclusions about the model performance. This is one conclusion from this. We'll also then go into the more recent reasoning models and looking whether the same problem persists there. So we saw that they can solve our older problem formulations very well, but we were again not sure whether this is maybe due to task set contamination as we released the problems in public in course of our studies. So we just created a small variation, again replacing the sisters, brothers with male, female friends. Same approach to test the models, and we see that even seemingly strong reasoning models that score highly on this test set benchmarks that I was showing before, again, exhibit this fluctuation. So we see clearly that the performance level on average goes up, yes, but the fact of existing fluctuations is still worrying. So the problem is still so simple that you should expect a rather uniform distribution across the capability to solve it, having the different variations in place. If you change the problem further, you see further ongoing difficulties even in the strongest models like O3 and O1 from OpenAI. Well, strong.
Jenia, as we're running very direct to 12 o'clock, you think we might get the chance to take one or two questions? So I don't want to stop you in the middle of everything, but just
I will take 2-3 minutes to finish. So rounding this up, we need to work on evaluation routines that make clear that what we actually assess from the model performance is true, and it's not creating an illusion of strong scores just because of contamination effects, for instance. So to wrap it up, the long-term goal of this line of research is to improve open foundation model scalability, and this requires interventions across the entire pipeline that has to be open for this reason. I was showing how to perform a comparison using the open pipelines and scaling law derivations here. The same methodology we can take now further up to the more complex systems that use these pre-trained foundation models as components. So on this agenda, we need to bind our efforts better, so to make sure we have critical mass of core ML experts binded in such studies, to have access to well-maintained, easily accessible supercomputing infrastructure, and also then to carry over the successes to domains, ensure exchange between core ML and applied fields. So there are some examples how other people try to do it. So this Anthropic initiative, binding efforts with US National Research Centers on the one hand, Open Frontier trying to bind open source community efforts on the other hand. Important to get attachment for sure there. As a reminder, take care about the compute time for such experiments. Apply for public funded facilities. Lion did this with quite success, so this is something any research lab can do. And we have now a couple of large European projects running in this direction. So hopefully this will have this binding effort. And we're hiring also along these lines. So please ping me if there is interest in such positions. So I would like to thank all the collaborators and especially, of course, the Lion community for backing up this line of research. Let's build this open pipelines together. And thanks for your attention, and sorry for stretching over the time.